Good morning, Vietnam. Welcome to the Wolfram Alpha Quantum Computing Framework Study Group here at Mankind and Training, hosted by me, Jeshua Parr. You know, uh, we've gone through quite a bit so far, several hours worth of material, but we started running essentially before we walked or crawled, for that matter. I'm gonna slow things down a bit tonight. We're gonna do a deep dive. I'm gonna do a lot of explaining. Got some definitions queued up. I'm gonna do some reading because we gotta have we need a good understanding of what we're even doing. I you a really good way to see at all what's happening. I do like the Matrix plot. I now that I understand what it is even, but when you should just when you make operators and states and things of that nature, you should look at their matrix form to really see what's going on. Um, so let's back up. We're gonna unpack. We're gonna learn tonight. We're gonna do some learning. So, uh, quantum field theory and the standard model of particle physics is broken things down as such. That's what we're doing with this quantum computing framework. We're making quantum states, uh, and we're using operators on those states in sequence. That's a circuit, and then we measure it, collapsing the entanglement, and you get a new state. So bosons are the force-carrying particles, like electrons, photons. They're purely energy, they're massless, and they do not obey the Pauli exclusion principle. Now, on the other hand, you have fermions. You are made out of fermions. I'm made out of fermions. They have matter, which the Higgs field gives a fermion. They do obey the Pauli exclusion principle, fermions. They're a half spin particle. And keep in mind H bar when you see H bar, that is Planck constant. It's just H over 2 pi. Now, the Pauli exclusion principle. So, two or more identical particles with half integer spins, so fermions, essentially, they cannot occupy the same quantum state in a quantum system simultaneously. So different quantum number, azimuthal number, the magnetic number, or the spin will be different. One of those properties will be different in uh in fermions in a system. Wave function is asymmetric for fermions, but it is symmetric for bosons. And with that, you have a base for the beginning of what we're looking at. So I have some more notes that I've taken for you guys. In quantum physics, a quantum state, which we should be familiar with, we've been manipulating quantum states in each one of these study sessions. It is a mathematical entity that provides a probability distribution for the outcomes of each possible measurement on a system. Knowledge of the quantum state together with rules for the system's evolution in time exhausts all that can be predicted about the system's behavior. A mixture of quantum states is again a quantum state. Quantum states that cannot be written as a mixture of other states are called pure quantum states, while all other states are called mixed quantum states. A pure quantum state can be represented by a ray in a Hilbert space over the complex numbers. I will go over what a Hilbert space is later. While mixed states are represented by density matrices, which are positive semi-definite operators that act on Hilbert spaces. Pure states are also known as state vectors or wave functions, the latter term applying particularly when they are represented as functions of position or momentum. For example, when dealing with the energy spectrum of the electron in a hydrogen atom, the relevant state vectors are identified by the principal quantum number, n. The angular momentum quantum number, L, the magnetic quantum number, m, and the spin z component, S sub z. For example, if the spin of an electron is measured in any direction with a Stern-Gerlach experiment, there are two possible results, up or down. The Hilbert space for the electron spin is therefore two-dimensional, constituting a qubit. A pure state here is represented by a two-dimensional complex vector, alpha beta. Alpha beta with a length of 1, that is, with alpha squared, beta squared equaling 0, where the absolutes of alpha and beta are a mixed state. In this case, a 2x2 matrix that is Hermitian and positive semi-definite and has trace 1. A more complicated case is given in a Brocket notation by the single state, which exemplifies the singlet state, which exemplifies quantum entanglement. Psi equaling 1 over root 2 up down minus the down up cats, which involves superposition of joint spin states for two particles with spin 1/2. The singlet state satisfies the property that if the particle spins which are measured along the same direction, then either the spin of the first particle is observed up and the spin of the second particle is observed down, or the first one is observed down and the second is observed up, both possibilities occurring with equal probability. A mixed quantum state corresponds to a probabilistic mixture of pure states. However, different distributions of pure states can generate equivalent, physically indistinguishable mixed states. The Schrödinger HJW theorem classifies the multitude of ways to write a given mixed state as a convex combination of pure states. Before a particular measurement is performed on a quantum system, the theory gives only a probability distribution for the outcome, and the form that this distribution takes is completely determined by the quantum state and the linear operators describing the measurement. Probability distributions for different measurements exhibit trade-offs exemplified by the uncertainty principle, state that implies a narrow spread of possible outcomes for one experiment necessarily implies a widespread possible outcomes for another. In the mathematical formulation of quantum mechanics, pure quantum states correspond to vectors in a Hilbert space, while each observable quantity, such as energy or momentum of a particle, is associated with a mathematical operator. The operator serves as a linear function which acts on the states of the system. So, if you remember, we've had quantum operators, quantum circuit operators, and those are how this is describing. There's with states, and we're operating on either the spin or the charge of a particle. The momentum. The eigenvalues of the operator correspond to the possible values of the observable. For example, it is possible to observe a particle with a momentum of 1 kilogram per meter squared if and only if the eigenvalues of the momentum operator is 1 kilogram meters per squared. The corresponding eigenvector, which physicists call an eigenstate, with the eigenvalue 1 kilogram per meter squared, would be like a quantum state with a definite, well-defined value of a momentum of 1 kilogram of meters per 1 kilogram meter squared, with no quantum uncertainty. If its momentum were measured, the result is guaranteed to be 1 kilogram per meter squared. On the other hand, a system in a superposition of multiple different eigenstates does in general have quantum uncertainty for the given observable. We can represent this linear combination of eigenstates. The coefficient which corresponds to a particular state in the linear combination is a complex number, thus allowing interference effects between the states. The coefficients are time-dependent. How a quantum state changes in time is governed by the time evolution operator. The symbols, the pipe, and the angle bracket surrounding the psi are part of the bracket notation, the Dirac notation. Statistical mixtures of states are a different type of linear combination. A statistical mixture of states is a statistical ensemble of independent systems. We've seen those too. When you see, when I ask for the matrix representation and it doesn't give me what I want, it gives me the bra and ket notation with an association to a sparse array for each of them. That's kind of what this is talking about here. Statistical mixtures represent a degree of knowledge, whilst the uncertainty within quantum mechanics is fundamental. Mathematically, a statistical mixture is not a combination using complex coefficients, but rather a combination using real-valued positive probabilities of different states, psi n, phi n. A number Pn represents the probability of a randomly selected system being in the state phi n. Unlike the linear combination case, each system is a definite eigenstate. In mathematics, Hilbert spaces, named after David Hilbert, allowed generalizing the methods of linear algebra and calculus from finite-dimensional Euclidean vector spaces to spaces that may be infinite-dimensional. Hilbert spaces arise naturally and frequently in mathematics and physics, typically as function spaces. Formally, a Hilbert space is a vector space equipped with an inner product that defines a distance function for which the space is a complete metric space. The earliest Hilbert spaces were studied from this point of view in the first decade of the 20th century by David Hilbert, Erhard Schmidt, and Friedrich. I'm not sure how to pronounce that. They are indispensable tools in the theories of partial differential equations, quantum mechanics, Fourier analysis, which includes applications to signal processing and heat transfer, ergodic theory, which forms the mathematical underpinning of thermodynamics. John von Neumann coined the term Hilbert space for the abstract concept that underlies many of these diverse applications. The success of Hilbert space methods ushered in a very fruitful era for functional analysis, apart from the classical Euclidean vector spaces. Examples of Hilbert spaces include spaces of square integrable function spaces of sequences, Sobolev spaces consisting of generalized functions, and Hardy spaces of holomorphic functions. Geometric intuition plays an important role in many aspects of Hilbert space theory. Exact analogs of the Pythagorean theorem and parallelogram law hold in a Hilbert space. At a deeper level, perpendicular projection onto a linear subspace or subspace, the analog of dropping the altitude of a triangle, plays a significant role in optimization problems as other aspects of the theory. An element of Hilbert space can be uniquely specified by its coordinates with respect to an orthonormal basis, in analogy with Cartesian coordinates in classical geometry. With this basis is countably infinite. It allows identifying Hilbert space with the space of infinite sequences that are square summable. The latter space is often the older literature referred to as the Hilbert space. Prior to the development of Hilbert spaces, other generalizations of Euclidean spaces were known to mathematicians and physicists in particular. The idea of an abstract linear space, vector space, has gained some traction towards the end of the 19th century. This is a space whose elements can be added together and multiplied by scalars, such as real or complex numbers, without necessarily identifying these elements with geometric vectors, such as position and momentum vectors in physical systems. Other objects studied by mathematicians at the turn of the 20th century, in particular, spaces of sequences, including series, and spaces of functions, can naturally be thought of as linear spaces. Functions, for instance, can be added together or multiplied by constant scalars, and these operations obey the algebraic laws satisfied by an addition and scalar multiplication of spatial vectors. In the first decade of the 20th century, parallel developments led to the introduction of Hilbert spaces. The first of these was the observation which arose during David Hilbert and Erhard Schmidt's study of integral equations that two square integral real valued functions f and g on an interval AB have an inner product, and there was some math that I was about to type in and I just didn't because I need to get on with the rest of the discussion. But so what all of this has said is we've talked about a quantum state, what makes a quantum state, everything essentially is a quantum state, a series of quantum states. It can be broken down into you are a collection of qubits in the series of quantum states. The Hilbert space is an abstract vector space which you can scalarly change objects in that space. It's an analog of a Euclidean space, but for matrices, for higher dimensional vectors. So we're going to come out here. Why are we doing this? Why are we studying quantum computing? It seems hopeless. What's the point? But there's been an explosion of all this interest, and when you have this many minds thinking about the same problem, there's bound to be leaps and bounds made. I have been vigorously exploring compilations of states, and it is absolutely incredible. Oh man, this quantum computing framework has given me the ability to do experimental physics without having a collider here. I need a quantum computer though, a real one. We need a quantum machine here in the lab, and I just don't know what to there I have so many ideas about how to increase dramatically the amount of qubits that we can entangle in a system and use as a computational basis. I have a tremendous amount of ideas, and in fact, I've spent the last 2 weeks with the ability now to study on a fundamental level how I want to design circuits then. How I should set up basis states for these systems that I'm trying to build, because the conventional named states are not going to do, I don't think. Uh, a lot of them are. I don't see there's a purpose for the Pauli matrices. There's a purpose for the rotations along X, Y, or Z. There's a purpose for phase, and there's a purpose for depolarizing and dampening amplitude. There is a purpose for the Fourier transform. There's a purpose for the Deutsch gate, the Toffoli gate. There's purposes for these, but as I suspect, though, that they won't be as useful in the system that I'm thinking of designing, as there are too many. You need to. So it could be thought of as you could just. I see. I don't like that idea that you can't. I want to be able to reset a lot faster than anyone thinks is possible. So, and I also want. So a lot of times a problem can be solved. A big problem can be solved by using a lot of solving bits and parts of it bit by bit and combining all of those results. Just a summation of what the bits that you could solve. And then you're left with not very much at the end, because the circuits were able to resolve so much of this problem. But I suspect that when you get into the hundreds of thousands of qubits that are entangled, you're going to want to design uh not I think, yeah, the implications for quantum mechanics are far different than the standard intuition that you would glean from trying to design a conventional circuit. I really think once we get lean in the direction of biological entities as a computing device, which is what we're going to have to call them once we get them correct. Once we have a functional quantum computer that's scalable, and you can sell them to people in their homes for a reasonable price. That is going to be where the world changes drastically. But it's like not there's not every problem can't be solved by quantum computers. Like there's most of the time conventional computers are just a better way to go about solving your problem in the first place. We're jumping through all these hoops to play tic-tac-toe with a quantum computer. There are roadblocks, especially with the fact that we're only at 1,000 qubits at best, and then when you do get your chance to shine, you get your 5 minutes with a quantum computer through IBM's experience, and you want to run some measurements, but you can only make circuits that support up to maybe 10 qubits at a time. So I suspect as we start to design circuits for mass entangled states, that the intricacies that are necessary in the gates that you have to design, they will go out the window at scale. So once you get up to 1,000,000 qubits in a system, say, and they're all entangled, we may be able to have a cyclic type cycles have not been uh, possible really because there's just only a linear operator way of doing a quantum circuit at the moment. But when there's that many qubits that are entangled along with other operator particles, I think it's a different ball game at that point. We need to think about designing it to streamline, to use as you know it's I need funding is what we need. I need to get my hands on hardware. I really need to look at this in person. I need to see a quantum computer, and I want to see what they're doing wrong, because I know we're doing something wrong. We should be able to entangle, because you are walking around and I am walking around and I am a large entangled system, and I stay entangled for until I until I'm not. I I believe when I'm in the ground, I'm still going to be stuck in this wave function. I don't know. I need to get my hands on hardware. So quantum computing is a type of computation whose operations can harness the phenomena of quantum mechanics, such as superposition, interference, and entanglement. Devices that perform quantum computations are known as quantum computers. Through current Though current quantum computers are too small to outperform usual classical computers for practical applications, larger realizations are believed to be capable of solving certain computational problems, such as integer factorization, which underlies RSA encryption, substantially faster than classical computers. The study of quantum computing is a subfield of quantum information science. There are several modes of quantum computation, with the most widely used being quantum circuits. Other models include quantum Turing machine, quantum annealing, adiabatic quantum computation. Most models are based on the quantum bit, or the qubit, which is somewhat analogous to the bit in classical computation. A qubit can be in a 1 or a 0 quantum state, or in a superposition of the 1 and 0 states. When it's measured, however, it is always a 0 or a 1. The probability of either outcome depends on the qubit's quantum state immediately prior to the measurement. One model that does not use qubits is continuous variable quantum computation. Efforts towards building a physical quantum computer focus on technologies such as transmons, ion traps, topological quantum computers, which aim to create high quality qubits. These qubits may be designed differently depending on the full quantum computer's computing model as to whether quantum logic gates, quantum annealing, or adiabatic quantum computation are employed. There are currently a number of significant obstacles to constructing a useful quantum computer. It is particularly difficult to maintain qubits' quantum states as they suffer from quantum decoherence. Quantum computers therefore require error correction. Any any computational problem that can be solved by a classical computer can also be solved by a quantum computer. Conversely, any problem that can be solved by a quantum computer can also be solved by a classical computer, at least in principle, given enough time. Other words, quantum computers obey the Church-Turing thesis, which means that while quantum computers provide no additional advantages over classical computers in terms of computability, quantum algorithms for certain problems have significantly lower time complexities than corresponding known classical algorithms. Notably, quantum computers are believed to be able to quickly solve certain problems that no classical computer could solve in any feasible amount of time. A feat known as quantum supremacy, the study of computational complexity of problems with respect to quantum computers, is known as quantum complexity theory, which is huge. So the quantum computing began in 1980. I think it was a little before that too. The idea uh was around before 1980. Paul Benioff proposed quantum mechanical model of the Turing machine. Feynman and Yuri Manin later suggested that a quantum computer had the potential to simulate things a classical computer could not feasibly do. In 1986, Feynman introduced an early version of the quantum circuit that notation. In 1994, Shor developed a quantum algorithm for finding the prime factors of an integer with the potential to decrypt RSA encrypted communications. 1998, Isaac Chung, Neil Gershenfeld, and Mark Kuberneck created the first two-qubit quantum computer that could perform computations. Despite ongoing experimental progress since the 1990s, most researchers believe that fault-tolerant quantum computing is still a rather distant dream. Duke University studies estimated that nearly 3 million qubits large fault-tolerant quantum computer could factor a 2048-bit integer in 5 months. In recent years, what now? Estimated that nearly 3 million qubits large fault-tolerant quantum computer could factor a 2048-bit integer in 5 months. In recent years, investment in quantum computing research has increased in the public and private sectors. On October 23rd of 2019, Google, in partnership with the Aeronautics NASA, claimed to have performed a quantum computation that was infeasible on any classical computer. But whether this claim was or is still valid is a topic of active research. In December of 2021, McKinsey and Company analysis states that the investment dollars are pouring in and the quantum computing startups are proliferating. They go on to note that while quantum computing promises to help businesses solve problems that are beyond reach in the speed of conventional high-performance computers, use cases are largely experimental and hypothetical at this early stage. Quantum circuits definition. Quantum logic gate, qubit, quantum state density matrix, mathematical formulation of quantum mechanics. This is a Toffoli gate right here. Oh, it even says, huh. I had recognized it because I've made enough of them. The prevailing model of quantum computation describes the computation in terms of network quantum logic gates. This model is a complex linear algebraic generalization of Boolean circuits. A memory consisting of n bits of information has 2 to the n possible states. A vector representing all memory states thus has 2 to the n entries, 1 for each state. This vector is viewed as a probability vector and represents the fact that the memory is to be found in a particular state. The bits of classical computers are not capable of being in superposition, so one entry must have a value of 100% probability of being in this state, and all other entries would be 0. In quantum mechanics, probability vectors can be generalized to density operators. The quantum state vector formalism is usually introduced first because it is conceptually simpler, and because it can be used instead of the density matrix formalism for pure states, where the whole quantum system is known. We begin by considering a simple memory consisting of 1 quantum bit. When measured, this memory may be found in one of 2 states, the 0 state or the 1 state. We may represent this state of memory using the direct notation, so that the 0 ket is 1 0 state, and the 1 ket is the 0 1 state. Quantum memory may then be found in any quantum superposition, psi, of the two classical states 0 and 1. Psi alpha is 0 and psi beta being 1. Alpha over beta, alpha squared, beta squared equals 1. The coefficients alpha and beta are complex numbers. The state psi is not itself a probability vector, but can be connected with a probability vector via the measurement operation. If the quantum memory is measured to determine whether the state is a 0 or a 1, this is known as the computational basis measurement. The 0 state would be observed with probability absolute value of a squared, and the 1 state with a probability absolute value of b squared. The numbers alpha and beta are called probability amplitudes. The state of this 1-qubit quantum memory can be manipulated by applying quantum logic gates, analogous to how classical memory can be manipulated with classical logic gates. One important gate for both classical and quantum computation is the NOT gate, which can be represented by a matrix. Mathematically, the application of such logic to a quantum state vector is modeled with matrix multiplication. The mathematics of single qubit gates can be extended to operate on multi-qubit quantum memories in two important ways. One is simply to select a qubit and apply that gate to the target qubit whilst leaving the remainder of the memory unaffected. Another way is to apply the gate to its target only if one other part of the memory is desired state. These two choices can be illustrated using another example. The possible states of a 2-qubit quantum memory are as follows. The ket 0, 0 is this vector here. The ket 0, 1 is this vector. The ket 1, 0 is this vector, and the ket 1, 1 is that vector. And all of these vectors make up the matrix of the C0 gate. As a mathematical consequence of this definition, C0, in other words, it applies a NOT gate X from before to the second qubit if and only if the first qubit is in the state 1. If the first qubit is 0, nothing is done to either. In summary, a quantum computation can be described as a network of quantum logic gates and measurements. However, any measurement can be deferred to the end of the quantum computation. Though this deferment may come at a computational cost. So most quantum circuits depict a network consisting only of quantum logic gates and no measurements. Any quantum computation, which is, in the above formalism, any unitary matrix of size 2 to the n by 2 to the n over n qubits, can be represented as a network of quantum logic gates from a fairly small family of gates. A choice of gate family that enables this construction is known as a universal gate set, since a computer that can run such circuits is a universal quantum computer. One common such set includes all single qubit gates as well as the C0 gate from above. This means that any quantum computation can be performed by executing a sequence of single qubit gates together with C0 gates. Though this gate set is infinite, it can be replaced with infinite gate set by appealing to the Solvay-Kichev theorem. Kichev quantum algorithms. progress in finding quantum algorithms typically focuses on this quantum circuit model, though exceptions like the quantum adiabatic algorithm exist. Quantum algorithms can be roughly categorized by the type of speedup achieved over corresponding classical algorithms. Quantum algorithms that offer more than a polynomial speedup over the best-known classical algorithm include Shor's algorithm for factoring and the related quantum algorithms for computing discrete logarithms, solving Pell's equation, and more generally, solving the hidden subgroup problem for abelian finite groups. These algorithms depend on the primitive of the quantum Fourier transform. No mathematical proof has been found that shows that an equally fast classical algorithm cannot be discovered, although this is considered unlikely. Certain oracle problems, such as Simon's problem and the Bernstein-Vazirani problem, do give provable speedups, though this is in the quantum query model, which is a restricted model where lower bounds are much easier to prove and doesn't necessarily translate to speedups for practical problems. Other problems include the simulation of quantum physical processes from chemistry and solid-state physics, the approximation of certain Jones polynomials, and the quantum algorithm for linear systems of equations have quantum algorithms appearing to give super polynomial speedups that are BQP complete. Because these problems are BQP complete, an equally fast classical algorithm for them would imply no quantum algorithm gives a super polynomial speedup, which is believed to be unlikely. Some quantum algorithms, like Grover's algorithm and the amplitude amplification, give polynomial speedups over corresponding classical algorithms. Though these algorithms give comparably modest quadratic speedup, they are widely applicable and thus give speedups for a wide range of problems. Many examples of provable quantum speedups for query problems are related to Grover's algorithm, include Broussard, Hoyer, and TAP's algorithm for finding collisions in 2-to-1 function, which uses Grover's algorithm, Farhi, Goldstone, and Gutmann's algorithm for evaluating NAND trees, which is a variant search problem. So they have a lot here on Wikipedia for quantum algorithms, actually. It's quite, and then a good C also section. They have a lot of information. So these quantum circuits, that's why I really want to get in to the lab here. I really want to get an actual quantum computer, even if it's just a small amount of qubits. We need to get a small system and build the rest of it. I really want to do actual computations, and I want to see what these speedups are. I want to see them. I want to run these algorithms, and I want to see the speedup. And I really want to see how it. I need to physically see. I know I can't see it, but I need to see what they're doing. I need to see the hardware of the quantum computer, because I'm certain with funding I can build a quantum computer with an outrageous amount of entangled qubits. I'm almost certain of it. I just need the funding to do so. And another thing, once the decoherence problem and the entanglement problem has a solution of a type, where error correction is not. We're never going to get a perfect system, but it's going to be not an issue because of the sheer amount of computational power once you do entangle that and compute it. I they are having problems. And it's not like I understand how like arrogant that sounds. Uh, this college student is certain that he can solve this problem, that we have the best minds in the world on this, and they've not figured out. Well, they figured out how to entangle them, but they even the biggest of corporations are coming out with they have a platform, launching platform, where they have deadlines to reach certain amounts of entanglement at a certain amount of entropy. I am certain we can surpass them here at Finley Analytics. I'm positive of that. We can surpass the current Google machine within 2 years. Give me 2 years, and I will have solved this problem. Give me 2 years. Give us 2 years, and we may have a working prototype. If if the if the foundational foundation works out in funding us, I have to speak to Jonathan about that again. But I it does sound like there is going to be an initial flux for the lab, which is nice. Jonathan did indeed say that Jonathan Hastro of the Foundational Foundation said, and I quote, that his mission from now on uh, in fundraising is to support the Origins project here at Finley Analytics. That is, he is he is a fundraiser, and he has said that his mission now is to fund us, which is lovely. But it's just me and a couple other people here, and I need more employees. I need equipment. I need measurement equipment. I need precision measurement equipment. And we need to build a quantum computer here, so I don't have to rely on hoping that IBM's not lying to me. So I'm going to pop over to hypergraphs now that I'm sorry for rambling. I know this is supposed to be about the quantum computational framework in Wolfram, but I had to stop for a moment because the quantum computational framework in Wolfram is kind of directly related to uh, we have been exploring the multi-way systems and trying to simulate the gravity problem. And what the hypergraphs in Wolfram seem to be saying is, so the black hole thing had some interesting implications with the singularity. Uh, but there are certain metric tensors and indices that you see when you project the hypergraph onto Brownian space. What we see is that the projection What was I trying to get at? What's that? There is, I am 100% positive that with the use of predetermined state qubits and then custom measurement operators or basis state, I but with the use of building these Wolfram quantum operators and quantum states, I I believe we found a roadmap to what we need to do. So you can keep building these states, and then the custom states you can operate on them and operate on them and operate on them until you see like what you need to do to build, because you know what the matrix representation of the quantum state. So, and you can build it state by state. You can build this element up from the ground, and the the research into that alone, there is going to be paper after paper after paper. I The academic papers will flow. There is a whole new branch of science that has come due to this quantum framework. So there will be a whole new field of research science, and it will be quantum informational states. I Like I was saying in the last yesterday, I by the time I graduate, there will probably be where I can get a master's in this quantum computational frame. I not in Wolfram particularly, but just in quantum computing. I or per, in or perhaps it just in theoretical quantum compute, like that. Maybe that will be a field itself too as well. So in mathematics, a hypergraph is a generalization of a graph in which an edge can join any number of vertices. In contrast, in an ordinary graph, an edge connects exactly two vertices. Formally, an undirected hypergraph H is a pair H equals X and E, where X is a set of elements called nodes or vertices, and E is a set of edges, non-empty subsets of X called hyperedges or edges. Therefore, E is a subset of P of X, where P of X is the power set of X, and the size of the vertex set is called the order of the hypergraph. The size of the edges set is the size of the hypergraph. A directed hypergraph differs in that its hyperedges are not sets, but ordered pairs of subsets of X. With each pair, and the reason I'm not going to read all of this actually, but it is important because these hypergraphs are are your quantum objects. Your quantum objects to the computer when it does these operations. That is what it's imagining, I guess, is it's working with a hypergraph, directed or non-directed. So like a, a basis state, or just a quantum basis, I suppose, uh, is just going to be a node or maybe a couple of nodes with they'll be connected, but they won't be directed. Where direction starts is in quantum operators, I imagine, is when we're going to start seeing a directed edge that has a certain weight, and that weight being the rotational operator of that qubit to this new state, is how I picture it anyway. and I may be seeing that wrong, but I don't. That makes sense to me as what I'm viewing is happening. So the reason I did bring this up is yes, because of how important hypergraphs actually are, and this is a new field of study in and of itself. The graph theory, the number and graph theory. There's specialists in number and graph theory. Uh, so I brought up this is another thing that you probably hear quite a bit, and it's out of context, and people don't know what they're talking about. This is a Lie algebra. A Lie bracket. Okay, in mathematics, a Lie algebra is a vector space G together with an operation called the Lie bracket, an alternating bilinear map, G by G, maps to G, that satisfies the Jacobi identity. The Lie bracket of two vectors x and y is denoted by xy. The vector space G together with this operation is a non-associative algebra, meaning that the Lie bracket is not necessarily associative. Lie algebras are closely related to Lie groups, which are groups that are also smooth manifolds. Any Lie group gives rise to a Lie algebra, which is its tangent space at the identity. Conversely, to any finite dimensional Lie algebra over real or complex numbers, there is a corresponding connected Lie group up to finite coverings. Lie's third theorem. The correspondence allows one to study the structure and classification of Lie groups in terms of Lie algebras. In physics, Lie groups appear as symmetry groups or physical systems, and their Lie algebras tangent vectors near the identity may be thought of as infinitesimal symmetry motions. Thus, Lie algebras and their representations are used extensively in physics, notably quantum mechanics and particle physics. An elementary example of this space of three-dimensional vectors, G equals R cubed, with the bracket operation defined by the cross product x times y. This skew symmetric since x times y equals negative y times x, and instead of associativity, it satisfies the Jacobi identity. This is the Lie algebra of the Lie group of rotations of space, and each vector v in R cubed may be pictured as an infinitesimal rotation along the axis v, with the velocity equal to the magnitude of v. The Lie bracket is a measure of the non-commutativity, non-commutative, commutative, ed, between two rotations. Since a rotation commutes with itself, we have an alternating property. X equals x times x equals 0. So the reason I brought this up is because Lie algebras are the rules that are defining a lot of these tensor products and matrices projecting onto Euclidean space or projecting onto Hilbert space. Sorry. Euclidean space is the analog that we think of. Uh, just a representation of a three-dimensional vector space. I actually, Lorentz invariance. All right. Lorentz invariance measures the universal features in a hypothetical loop quantum gravity universe. The various hypothetical loop quantum gravity universe design models could have various general covariant principal results. So where's the definition? They don't have much about it. Okay, so yeah. What else were we gonna look at? I wanted to. I did want to. There's something else that I thought was important. Um. Anyway, we'll cut over. So let's see here. What do I want to look at? Evolutions of systems as a system evolves, and then their probabilities, amplitudes. So this is a simulated system of a series of branches from a single event at one, and as it disperses, its probability broke out at one half each, and then that's a tree that broke out at a quarter each. And this is simulating, this is branchial space, what we're looking at here. An evolution of the system evolving in branchial space. And then I made an array plot of this branchial space, and this is what it looks like. Those are the data points. Here is a different system where we have a charge, a negative charged electron, and then we have a positive density over here, a proton, up quark, two up quarks and a down quark. And then over here we have the electron cloud. And then it is more likely it more times divulged over to the proton side, the positively charged density. As you can see, because there's more causal branches over here, whereas it it far less of the time it was attracted back out to the electron cloud. I had here's good examples of operators. Another multi-way system causal graph. Here's a Schmidt decomposition. This is a good example of taking a state and decomposing it back out to its origin basis states. And then asking for the amplitudes. Right. The element associations for it. And then the second basis. Not this basis, but that one. That's the element association. And then you can ask it for so I made two states here, and you can ask for the distance in the Hilbert space between the two states. What is the distance in Hilbert space between these two states? And it returns it. And then I did it again here. And now I'm asking for the quantum distance in. I don't think that's in Hilbert space, though. I think that's in real vector space. Or no, that may just be like I was saying earlier. There's four different measures of a quantum state, and any difference and no two fermions can be in the same state in the same system. So there's going to be a slight difference in state, and that's been given to a number and called fidelity between these two states. There's a fidelity of 0.71. And then there are commands I do think to increase the accuracy there. I asked for the fidelity of several different combinations of the states there. Um, because these two states were not what I created. Okay, yeah, those mixed states have imaginary parts. Quantum Schmidt decomp. So now I'm asking for the block sphere distance between these two states and the block sphere representation. And it gives you an exact numerical distance. This gave me that, and I said I need a numerical distance, and it was like, okay, here's the numerical distance. And then I asked to increase the accuracy. Increase precision. That's amazing. I'm not sure what the command is there. I'll have to look it up. Asking for the Hilbert quantum distance, asking for the Beer's angle quantum distance, and asking for trace distance. Asking for the relative entropy, von Neumann entropy. Asking for quantum distance fidelity. The states are mixed, so it was a big mess. What am I asking for here? Yeah. All right, what else did I have for you guys? Certainly to keep, like, just for instance, certainly to keep up on this. Hmm. All right. So when we make these operators here, a good way I've found. So you see on the matrix plot, this is a higher dimensional object because Deutsch is three-dimensional. Um, let's go. There. As you can see here, we got on states and then these imaginary states in the last two positions, four positions. They fill the last four. So really right now? Why does it do that? All right. And there's what Z rotation looks like. And then let's just go. Let's look at that there. Try to assume that. Yeah, no, I didn't think it was gonna. Okay. There we go. That's what I was looking for. Will that work? Oh, that did something different. Okay, so maybe not. Anyway, so we got a 4 here, a 2 here, a -2 here, and a -4 here. And that's the Pauli Z matrix. And then when you do a Z rotation operator, it's gonna Huh. Oh, that's weird. Huh. Okay. Yeah, I guess that makes sense. So do what I should do is that maybe? No, it doesn't seem to change it at all. So that's what that looks like. If you want to see what's actually going on when you make these operators and these states, look at their matrix or look at their like element association. Zeros, Ket and Bra correspond to that position. The 0 and 1 correspond to the next position over. They are keyed to that distribution. So let's do that. Let's go with that. Uh, I see. So here we go. There's the state vector for it. Matrix. All right. There we go. This is the all important foyer. All important foyer transform. What a CT looks like. And then I just want to, for sake of educational purposes, I gotta wrap this up. I've probably been way over time. I'm probably way over an hour, but I just want to do this real quick. Show that you can. So I just made this custom matrix to represent my custom rotation on theta, and I'm using the alpha and beta states to make this quantum operator. And so do that and then go there we go. There we go. Oh, that's weird. It didn't change anything at all. It didn't keep my changes at all whatsoever. So I guess in this framework, that's probably a bug that they're gonna have to fix. Because that if I make this object, if I make this using a visual object like that, and I change parameters in it, it should make a new state with those parameters. That not just a snap picture of its initial what was copied to start the matrix. I That's odd. That's very weird. Um, that's what I want. Man, I can't believe I forgot about that. The measurements. Um, I can't believe I forgot about the measurements. Hmm. Oh, because it's a random. It, really? That's weird. But this is like so. I took a measurement. Oh, the simulated measurement. I wanted to. So that's how you do a simulated measurement, and it'll give you. It was either 1 or 0 on any of these kets. It'll give you a distribution of some kind. random univariate distribution. I want to figure out why that didn't work. Oh, and then this is where were we at here? This is the maximally entangled state superpositions. It's either off or it's either all on. Thank you guys for watching. I've been way over on time, I'm sure. So I'll be back tomorrow. There will be two more after that, but then we're wrapping the class up for now. Maybe there will be another one later on down the line, but I think I've covered already most all of the functions in here. I'm just gonna keep for the next several classes, I'm going to keep harping on what it is that you're even doing. So you make this operator do this on this on this, and then you see the picture and you're like, oh, okay, and then you do something else. Well, what did you just do? What is it that you did? Look at the original basis state, and then now look at your qubit after you've done this operation to it. Or now look at the matrix's state now that you've done your operation. What is going on in the matrix? What is happening there? Just pay attention. Pay attention. Thank you guys for watching. I will be back, like I said, tomorrow. And I'll see you there.